Hello, folks joining in. Let me know who you are so I can take attendance. Hi, Sarah. Hi, Dominic. Hi, Merla. Hi, Riley. Hi, Nicholas. Okay, others just joining in, say hello so I know who you are and I can give you points for participating. We're going to get to our agenda once I get at least half of you here. And we've got a few more joining us. Super. Type in so I know who you are. I got a bunch. Deacon, hello. Larissa and Lee. Dynamite. Glad you could all join me. And I got some more. I got Vincent, Isabella, Priya, and Natalie. Super. And I've got Lily. Good. Others just joining us, say hello so I know that I've got you. Yes, Leah, that's fine. Okay. All right. Others, when they join in, let's say hello so I know who you are. But we can just about start now here. Let me tell you what's up for this hour. Okay, Shilpa's here. Good. What's up is that we're going to take your questions first on two things. On the Tuning Fork Lab, if you have any questions, because I'll collect them. Maybe I already collected them. I don't remember. But if not, I'll see if you got a question on that. And second of all, on the BAT assignment that you have. Okay. Good. I got Noah here as well. Super. And let's begin. Tadashi, hello, welcome. So, do you have any questions, folks, on the Tuning Fork Lab? I know I think some of you turned it in already, maybe a lot of you, but I forgot to look in my folder before I started here to see if I have them. Do you understand what needs to be in it? So, one set of work for each formula, but work out all the values for every formula. So the one set you'll show and the rest you can do on your calculator and put in a table, the results. Tuning forks, frequency, the percent error, and so on. Your conclusion's really short. And hi, Ollie. Your conclusions, just tell me what you got. Tuning fork one was whatever, was, okay? That's pretty much it. So are you set on the Tuning Fork Lab? If you are, that's great. If you got any last questions, this is your final chance. And I'm going to just make sure I don't have others out there. So I'm still looking for Magdalena and Julian K and Aiden K, Julian L, Lena, Tom, Christian, and that's it. And Magdalena's there. Good, that makes most of you. So thanks for coming. And yeah, this will be our last time of the year. Let's make some good use of it. I got some stuff to show you too when we're done. But let's turn our attention to the BAT sheet. Now, let's see if you got any questions on the problems for the BAT worksheet. Let me go grab one while you're grabbing yours, okay? See if you got stuck somewhere, and this is your chance to ask me. Okay. Yes, we got a question. All right, so about C, I wasn't entirely sure how to do it, and I know some other people are having the same issue. Okay, me too. To Dominic? I don't quite get that. Tom is here and Julian L are here. Let me write you down, you two. Glad you could join us. Tom is here. Julian is here. Julian L. That's good. So I'm just missing Christian, Lena, Aiden, Julian K, and that's it. That's pretty good. All right, and then Magdalena has a question too. It says for A, how many frequencies and how many mediums should we find the wavelengths? And can we submit the assignment after the live stream? Marla asked, and the answer is yes. Okay, so here we go. I can't find the sheet, so I'm going to have to ask your help a little bit. Lena, hello, welcome. Thank you for joining us. Dynamite. So let's go to Lily's question first. Okay, and we're getting other questions too. Yes, you can. I hate to have you take a picture of it. I'd rather have you scan it if you can. Scan it and upload it to Google Classroom. Please don't just email it to me because that's not a real fun way for me to grade. But I'll do it if you can't have any other, if you can't figure out any other way. Well, let's go back to Lily's question. So she wasn't sure entirely how to do it. I know some people are having the same issue. Okay, Lily and everyone, I don't have the sheet with me, so I can go get it on my computer, but then I'm a little distracted, so that's going to waste some time. So instead, I'm going to ask you, is C the one where you're trying to figure out with the bat hearing 0.001 milliseconds or something like that, what that tells us about the bat? So what is C? Can you guys help me out a little bit with C? Well, let me answer A first then while we're doing this. Okay, got it. Okay, so let's go for C. C is the one the bat's cries about 5 meters away. Okay, so C, a moth hears a bat's cry. For how long does the take to return to the bat from the moth? Okay, so for the bat being 5 meters away, we need to know time, right? So here we go. So it's 5.0 meters away, and I want to know the time. And I assume it's at 20 degrees. Thank you, everybody, for typing that, and I appreciate it. Sorry I don't have that sheet, but it's at school, as so many things are. So what we need is to kind of think of this way. Velocity of sound is a constant. So we got this old equation. Remember this one? Velocity is distance over time. Let's switch these two. So we got time equals d over v. Well, what's the distance? Hey, we got it. Boop, 5 meters. The velocity, we got that too. What's the velocity at that temperature for sound? I assume it's 20, so somebody throw a number my way. What's the velocity? Somebody got V for me? What's the velocity of sound? It's on that sheet, and I want to use the data you got. 344. Okay, so let's take that. So the time is 5.0 meters divided by 344 meters per second. Good. Give me the time, please. So crunch it out. It's going to be something small. 0. what? I don't know, 0.0 something or 00 something. So can you guys do that and get me the time? And then we can more or less answer the question. Okay. And here we go. It's a bat and a bug. So here's the bug. And here's the bat. I'm not a very good bat drawer. Bat, bug. And this is 5 meters. Okay, you got it? Thank you all for doing that. So, oh, I got 2 different answers though. It's some of you got it in milliseconds and some of you got it in seconds, but you got different stuff. Okay, 5, oh, it's going to be 0.01. I'm not sure it's going to be 0.029 seconds. Natalie, that seems odd. But we can do, okay, Marilyn, you erased yours, but I think this might be right. So 14.5 milliseconds, or you can say 0.00145 seconds. Is that right? It's 0.0. Okay, so just 10. Okay, now it's nice that Magdalena changed it into milliseconds. So 1, 2, 3, or 14.5 milliseconds. Why? Look at the next problem. Ah, okay, gotcha. The sound was there and back. Thank you. Okay, good. That makes sense. Good. Thank you, Natalie. So she said the sound is there and back, so she doubled the time. So 14, and I'll write 14.5 milliseconds one way, or 29.0 milliseconds round trip. Now, I'm not sure how the question's worded, but more or less, once this gets sent out and hits the bat, really it's only one way. So I would think it'd be more like this one. You know what I'm saying? But it depends how the question's worded. And would it be 15 because of sig figs? Could be. I don't have it in front of me. Could be. So here's the deal. Look at the next question, I think. Is that the one where it says a bat can hear differences of 0.1 or 0.01 milliseconds? Is that something like that? So what can a bat hear? Differences of what time period? Ah, Julian K showed up. Please be on time in January, but I'll say next year. .1 milliseconds. So if a bat can hear 0.1 milliseconds, is there any problem with a bat hearing 14.5 milliseconds? No problem at all. So that time difference is no problem. You know what I'm saying? So bats are really good at hearing small differences of time. So that time change of 14.5 milliseconds, a bat can register that in its brain and know essentially where the bug is, where the bug is. What else can I help you out on the bat problems with? And try and be specific, and you may have to give me some numbers. Anything else on the bat sheet you want to ask about? Any more bat questions? Or are you feeling bat happy about this? Or is it driving you batty? Can we go over B? Yes, we can, Isabella. And you're going to have to remind me what B is. Magdalena asked for A again. A and B. Okay, well, let's see. For A, how many frequencies and how many mediums should we find the wavelengths? For all of them. So for A, your waves are going through air, so it's air only. That's the only medium because the bats are not flying underwater or going through concrete or something like that. So Magdalena, you don't need to do it for any other mediums, just for air. But they want you to do it for the wavelengths in the range that they can hear. But do entire range. So do the first hertz they can hear, and do the last. And then you got it, right? You don't have to do the numbers in between because you just give it as a range. So, and it's at 20 degrees exactly. So I guess you can use whatever they said, 344 meters per second. So again, here we go. What are we doing? We want the frequency. So here's our equation. Velocity, the equation you're using is the wave equation, right? Velocity is wavelength times frequency. Well, you want frequency, just like you did in the tuning fork lab. So it's V over wavelength. So chuck it in there, folks. So the V is what? 344 meters per second divided by the wavelength. Now, I don't remember the wavelengths they gave you, so you're going to have to put those numbers in there in meters. And then you can just do it. So put that in, that'll be in meters, and then you'll get the frequencies the bat can hear. Got to put the wavelength of echo frequency used by bat at 20 degrees. Yeah, that's it. So it's going to be that, and I'm going to do it twice. I'm going to do it with the first, if they gave you wavelength, I'm sorry, okay, if they gave you wavelength, then the first wavelength, and then the last wavelength, and then find the two different frequencies, and you got the range of hearing in frequencies, in hertz, of a bat. Oh man, okay, well, let's see, Lily says we're finding the wavelengths. Okay, but then the frequencies must be given. Oh man, okay, all right, I misunderstood your question. I wish I had it in front of me, but I just don't. So it's the same equation, the same idea. Yeah, exactly. So it would be, to get the wavelength, it's going to be V over F. So this is 344 meters per second. And this is the first one, then the second one. So you're going to use this equation twice. Well, I'll say the last one. You got it, folks? So just use that twice, and it'll come out in meters then. You get two different answers in meters. There are 18,016 hertz. Great. So first one, 18,000 we put in. And the other one we put in 16. And I'm not going to do that for you because you can certainly calculate as well as I can by dividing 344 by one number and then 344 by the other. Then you've got the range of wavelengths from that many meters to this many meters. Is that okay? Hope you can do that. So there's your equation, right? We need to know that wave equation. That'll be important in other physics classes you take. Okay. All right. Okay, anything else on the bat sheet? Can we go over E? Yes, and Priya also says E. Okay, E, excellent. So write out a little bit of what E is to refresh my memory. Yes, I've done it before, but I've got to have your help to remind me of the wording on E. I'll try to be a little more clear writing on the board. All right, what's E about? Thank you. Why bats cut out in short bursts if they know the insect is close, longer burst if the insect is further away. Okay, I'm the bat. You ready? I know, I don't have any pride. Here we go. Here's the bug. You tell me why a bat does this. Ready? Why is it going to do that? Why do they do that? They send out short bursts first, but then they send out a lot of bursts when it gets closer. Why? Let me do that again. I'm eating the bug at the end of the time. It takes energy for the bat to send those bursts out. So please stop laughing at my behavior and write something. It's not about taking much longer, Larissa, because it's not really very far away. So it's more to do with, yes, Magdalena. Okay, so they can get a way detailed picture of where the bug is. Okay, so watch again. Okay, I know from my feedback the bug's somewhere out here. I'm going to go in this direction. But I want to get the bug exactly in my mouth. So watch when I get closer. All right? When it gets closer, I got to get a more detailed picture of exactly where it is, as Magdalena described. Hello, Ryan. So once you have that detailed picture, then of course the bat can get it right in its mouth because the bats aren't that big. Okay? Lily, it's less about the numbers and more about the amount of feedback. Far away, I just need to know what direction to go. Right? I need to know I got to go roughly that way. But when it's really close, I need a lot of feedback to know right where that is so I can get the bat exactly in my mouth. So it's about the amount of feedback that the bat is getting. More bursts, more feedback. Okay, so you guys write something about that. Did that help? I hope. And anything else I can do for you on the bat sheet or in the bat department? Because we got some other physics we're going to do. Bats are pretty cool, aren't they? Don't you love that? They really can measure, so to speak, in their brain a very short distance of time. Have you already gone over D? I don't know what D is. So type in a little bit of D, Shilpa, and let's see if I have talked about it already or not. I do not remember what D is. I'm not sure I follow your comment, Magdalena. One could also say that for E, that the bat needs to hear the echo and so cannot make noise itself to be able to listen. No, it's more like the amount of burst. Okay, watch me. Okay, I'm sending out a burst, and so I know the bug's out there somewhere. I don't know quite exactly where. I'm getting closer. I want to position my flying so I fly right to the bug. I need more information. I need more pictures to tell me exactly where that bat is. Now I'm getting really close. Lots of burst because I need exact detailed information of where that bug is so I can eat it. Okay? So don't get too worried about numbers in this case. It's more like how much feedback does the bat need? I don't need much. I just got to go in that direction of the bug. But when I get closer, I need a lot more feedback to know exactly the location of that bug. Okay? All right, so let's go back to D. Shilpa, thank you for writing this in. Bats can detect a time difference of 0.1 milliseconds. So explain using your answer to C. Yeah, we kind of already did that. Remember, our answer to C was like what? For the bat, there's the bat. For the bat to the bug, took like what, 15 milliseconds or something like that. And the bat can hear differences of 0.1. So what's the bat say? Hey, I can hear differences of 0.1 milliseconds. So 15 milliseconds is no problem at all, right? So 15 milliseconds, no problem to hear this feedback, this echolocation. Remember what it's doing. And it's sending out a specific wave. The wave hits this and then comes back, right? It's echoing off the thing. So if it comes back and it takes 15 milliseconds, and the bat could hear where it is, if it's even 0.1 milliseconds, then 15 is no problem for the bat. They have way more capability than that. Okay, they can easily see things that are much closer to the bat and have much less of a time difference for the wave to hit the bug and come back. All right, so yes, yes. Okay, bats away. The next thing I'd like to do with you, if we're done being batty, is to talk about the Tacoma Narrows one last time. So recall, Tacoma Narrows Bridge, for those that were there, and I hope for Meryl I sent you like a link to a video at least. I think I did. Here's the two towers, and here's the suspension bridge in between. Remember that, everybody? Okay, and remember how this thing went up and down? Now, I know Tadashi's out there. Tadashi, you can maybe remind me that up and down was an example of what sort of thing in physics? Let's see if Tadashi can remember, because I think he and I did it together with that steel bed spring. So what's that as an example of? What formed in the Tacoma Narrows Bridge because of the wind? Yeah, you can check your notes, Tadashi. That's good. Check your notes and see. Let me open it up to others. So he's going to find it, and others find it as well. So what is that? What forms from the wind coming in and hitting this bridge? Remember, there's cables coming down too here. But basically, it's the two towers and the bridge that I'm most interested in. Yes, thank you, Tadashi, and others got it as well. Good. So a standing wave has been set up. So, okay, so and I'm going to make my picture even more messy. Where somebody else besides Tadashi, where was the antinode? You want it at the tower or you want it in the middle? Where do you want the antinode, somebody? Remember, standing waves got nodes and antinodes and they don't move, and I want to know where they're at. So some of you are typing, including Tom and Lee, so type a little bit more, and Shilpa and everybody. Okay, antinodes in the middle. Hey, lots of feedback. Thank you, Sarah. Thank you, Lily. So I'm going to put an A here. And these are where the nodes are, right? I can put it here. Node. Okay? That's a standing wave. And then we had a second one that I won't try and draw there. Do you remember when it didn't just do this, it also did this on that particular day that it broke up, right? So a standing wave was set up by the wind then a second type or second standing wave. At the antinodes, folks, this is where the is concentrated. What's concentrated at the antinodes? What's concentrated at the antinodes? And Deacon answered too. Thank you, Deacon. The energy. Thanks, Tom. Thanks, Sarah. So what that means is I had energy here, and then once it started doing this, I had way too much energy on the sides of the bridge. Remember, the bridge is like this, but it also started to do this motion. And all that energy at the antinodes probably broke up the bridge. So energy concentrated at antinodes broke up bridge. Why did I write a 1 there? Well, you could probably guess. There's a 2. And I'm going to erase this bat stuff and talk to you about the 2 as well. Or another theory or another way of describing the physics of this, okay? And thanks for everybody participating, even if I don't acknowledge you. Thanks for typing in. Keep doing that. So I may have the one way the bridge was destroyed is a standing wave, okay? Maybe a standing wave was set up and then another one, so much so that the energy at the antinodes broke up the bridge. Or the other way we said is that what else could have happened at the bridge? So, or for number 2, the wind from a certain direction, sorry, that's certain direction one day the wind from a certain direction caused the bridge to so if I don't use the idea of standing waves, what is it that I'm going to use here instead? The wind caused the bridge to do what? So forget about the standing wave. What's another theory about what happened to this bridge? They didn't say the word on the film, but I think you know it. Lee knows it. Let's see if some others have typed it in as well. Thank you, Lee. Cause the bridge to resonate. Now, remember when we had resonance? Okay, Deacon and Lily as well. Super, good. Remember when we have a resonance, we have a lot of transferred from one thing to the other. In this case, from the wind. So recall, during resonance, a lot of is transferred. Oh, look at that. You guys are quicker than me. I can't even ask it again. You already got it. Magdalena's got it. Okay. A lot of energy is transferred. That is so it. And what's the deal? So much energy that what did it do? So much energy was transferred to the bridge that So the bridge resonated so much that it broke. Now, to be honest, some of the engineers who did this bridge weren't really all that smart, or collapse. That's a better word, Riley. Because this had happened before. You ready? You guys might know this already. I think it was in Europe, and I don't know where, and I don't know when. I want to say the 1800s, but somebody can Google it and find out. So here's what happened. I had a bridge, and it wasn't a suspension bridge, but it was a bridge. And I had a bunch of soldiers crossing this bridge, and they were all marching in step. Hoop, lift, 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 right, lift, lift, right, lift. Okay. Hundreds of them. Unfortunately, it matched the of the bridge. So I'll say 1800s, soldiers marching. I don't know if I talked about this or not. Matched the of another bridge. Yeah, frequency or better, Sarah, right. Natural frequency, and Tadashi has it as well. That's right. Kind of like it was matched out here years later by the wind, okay? Here it was matched by people marching. The natural frequency of the bridge. I'm going to abbreviate freq like that. And big surprise, what did it do? It accepted more energy, and this bridge did what? While these people were on it, by the way. And I like the Riley word. We're going to use that this time. Good. Marila's in there too. And Julian, which Julian? Julian K. Okay, so this bridge earlier than the Tacoma Narrows, right, collapsed due to resonance, right? Okay, but I should write that. To resonance. So resonance is not always a good thing, okay? Guess what they tell soldiers today when they're crossing a bridge? Ooh, Shilpa found it, 1826. Thanks, Shilpa. You're on the stick. I love it. Great. So at least I was kind of right, 1800s. Okay, so what do they tell soldiers to do today? Exactly, not to march in rhythm. What they call it in English is, all right, everybody, break step. Break step means just walk however you want to walk, different from everybody else. Break step, yeah, in a like random way. And that way they don't cause any bridges to resonate. They still do that today, so they don't collapse bridges. Right? Kind of cool, huh? So if you got a bridge, resonance is something you may want to avoid. Okay. But sometimes resonance is fun. Okay. Resonance isn't always a bad thing. I got something now, and I'm going to do this with you, although I'm not sure if you're going to see it because I got to do it over my head. And this thing's, I call it a flugelhorn. I don't know what it really is. It's like a piece of plastic pipe with a hole. All right. See those? Hole at both ends. Okay. I hope I can erase this. You got all that. You're fast writers. I'll send you the video anyway. So how are we doing on time? We still got a few minutes. I got two things to show you in our last few minutes. One is this flugelhorn. So I guess you got to listen. You ready? Whoa, sorry, hit the computer. Okay, this thing resonates, but only at specific frequencies. So some musical instruments, I know this is not like a great instrument, some instruments will resonate at more than one frequency, okay? And you got your columns of air to resonate, right, from the tuning forks in the lab. And you might have realized there's more than one spot where you can get a loud noise. And one is the main spot. That's the one you guys found, but there are other ones that resonate a little bit as well. So, isn't that cool? So sometimes resonance can make some nice sounds. And notice nothing in between, only one pitch or the next one, but nothing in between. So resonance can be kind of a good thing, a fun thing as well. So it's not that it's good or bad always. Then I got this, an old cheap drum that somebody made. Okay. I don't know if some of you play the drums or not. Do I have any drummers in the school band or on your own? Michael Ward says it's called a whirly tube. That's nice too. Okay, so I got two names for it, whirly tube or a flugelhorn. Okay. Thank you, Michael. And Michael, you should watch Tacoma Narrows Bridge video, by the way. Google it and watch it. It's only a few minutes. Okay, if I tap this, it's not that it's resonating, but instead, what I set up is what? So now we did this, for example, I'll just tell you, Tadashi and I did this in 2 dimensions, no, in 1 dimension with a spring, with a bed spring. This does it in 2 dimensions. What am I setting up here in a drum, just like any drum somebody plays in the band? It's not really a forced vibration. Hint, it's moving a lot in the center of the membrane, isn't it? So watch in slow motion. Down, up, down, up. What have I set up here? Down, up, down, up. And hint, it's not moving around the edge. So here, I still got 3 minutes. Here, it's not moving. So at edge, no movement. But the middle part is going up and down a lot. So what is it that I've made here? Think Tacoma Narrows Bridge, but in 2 dimensions instead of 1. Right? A road is close to think of it, and you think of that as 1 dimension. Okay? Tacoma Narrows. So without thinking about resonance, what else could be happening that's happening in the drum or any drum in the band? What am I setting up? I'm doing this to talk about these 2 concepts, right? Resonance, which we just talked about with the bridge, and we said there's an alternate explanation for the Tacoma Narrows Bridge. What was it? And what am I setting up here as well? That's going up and down quite a lot, right? So that goes up and down. And the edge of the thing is not moving. Nobody's got it. All right. This is, in the middle, folks, an antinode. And on the edge, at edge, we've got a node. So the node's this whole thing. That whole thing is a circular node. So node is the whole edge. Makes sense, right? It's not moving. And when the thing's actually vibrating, better than a cheap drum like this one, it's going up and down a lot. The membrane of the drum is vibrating up and down, right? So that's going up and down, and there you go. So a standing wave is what I'm trying to say. So in a drum, we get a standing wave setup. Every drum. set up. And we're out of town, Well, I'm out of town. We're out of time, and okay, that's fine. I wish you all good holidays. I'll contact you in January, so I'll see you next year. Have a good rest of this year, good holidays, and thanks for joining me, including our guests today as well. All right, so goodbye. Bis nächstes Jahr. Thank you.